created by Mindsticks Foundation Trust. Hello students, welcome to today's Explainer. Today we are going to be covering 4 main topics. We'll start with the basics of similar triangles, move on to the area theorem, then tackle solving example problems, and finally wrap up with mastering complex proofs. Let's get right into it. Section 1. Basics of similar triangles. It's always good to quickly refresh our memory on the foundational rules of similarity before moving on to the heavier stuff. Let's take a look at a very practical, everyday example. Imagine we have 2 poles standing perfectly straight, completely perpendicular to the flat ground. The smaller pole is 4 meters tall, and the larger one is 8 meters. Now, because the sun is shining on them at the exact same time of day, that smaller pole casts a 6-meter shadow. If we draw a line joining the top of the poles to the very tip of their shadows, we suddenly have 2 right-angled triangles, triangle PRQ and triangle ACB. So here's a question for you to really think about. How do we actually know these 2 triangles are mathematically similar? Well, think about it. The poles are perfectly vertical, right? So angle R and angle C are exactly 90 degrees, no doubt about that. And since these shadows are being cast at the exact same moment, the sun's angle of elevation is absolutely identical for both. That means angle P and angle A are equal too. So thanks to the angle-angle, or AA test of similarity, we know for sure these triangles are similar. Keep this AA test in mind, it's going to be super important for us today. All right, moving on to section 2, the area theorem. Now that we're all warmed up, let's formally introduce the absolute core theorem of today's lesson. Here is the theorem we'll be focusing on. When 2 triangles are similar, the ratio of areas of those triangles is equal to the ratio of the squares of their corresponding sides. Pay really close attention to that last part. We are comparing the ratio of the areas directly to the squares of their corresponding sides. It's not just the sides themselves, students. It's the square of those sides. That is absolutely crucial. To really grasp why this theorem is true, let's look closely at these 2 triangles on the screen. We're starting with the fact that triangle ABC is already similar to triangle PQR. Now, to figure out their areas, we obviously need their heights. So we've gone ahead and drawn a perpendicular height AD, dropping down to base BC, and another perpendicular height PS, dropping down to base QR. And just like that, we've got all the pieces we need to prove our theorem. Let's just walk through the logic of this proof step by step. It's actually quite beautiful. Step 1, we just write down the basic ratio of their areas. We all know area is half base times height. The halves cancel each other out right away, leaving us with base BC times height AD divided by base QR times height PS. Pretty straightforward, right? Okay, step 2. Focus on those smaller inner triangles on the left side, triangle ABD and triangle PQS. Angle B is equal to angle Q because the big main triangles are similar, and both angle ADB and angle PSQ are perfectly 90 degrees. So using that AA test we talked about earlier, these inner triangles are similar too. Because of that, in step 3, the ratio of their heights, AD over PS, is exactly equal to the ratio of their sides, AB over PQ. So when we swap out the height ratio for the side ratio in our first equation, we end up multiplying the side ratios together. AB times AB becomes AB squared. And there you have it. The area ratio becomes the square of the corresponding sides. The proof all falls right into place. Let's move on to section 3, solving example problems. It is time to take this theorem and put it into some practical use. So let's methodically break down a problem together. We'll split up what we already know from what we need to figure out. For our knowns, we have the ratio of corresponding sides of 2 similar triangles, which is 2 to 5. We also know the area of the smaller triangle is 64 square centimeters. What's the unknown? Well, we need to find the exact area of the bigger triangle. I'll guide you through the calculation here. Let's assume triangle ABC is our smaller one, and triangle PQR is the big one. Now we just apply our newly proven area theorem. The ratio of area ABC to area PQR equals the square of their side ratio. So we take that side ratio of 2 by 5, and we square the whole thing. 2 squared is 4, and 5 squared is 25. That gives us a brand new area ratio of 4 by 25. From here, we just substitute that known area of 64 for the smaller triangle and simply cross-multiply. So 64 multiplied by 25 divided by 4. If you divide 64 by 4, you get 16, and 16 multiplied by 25 gives us exactly 400. That means the area of the bigger triangle is 400 square centimeters. And please always remember to state your units clearly when you're doing geometry. All right, finally, section 4, mastering complex proofs. Let's see what happens when we apply these rules to a much more complex shape. Take a good look at this shape, trapezium ABC. The special thing about a trapezium is that exactly one pair of opposite sides is parallel. In this case, side AB is strictly parallel to side CD. On top of that, the diagonals AC and BD are intersecting each other right at point P in the middle. Our goal is to find the ratio of the areas of the top triangle APB and the bottom triangle CPD. But first, we have to prove they're similar. Let's list out our angles. Since line AB is parallel to line CD and line AC acts as a transversal crossing them, angle PAB and angle PCD are alternate interior angles. That means they are equal. Also, angle APB and angle CPD are vertically opposite angles, making them equal too. So, once again, using the AA test of similarity, we can conclusively say that triangle APB is similar to triangle CPD. And now that we've successfully proven those two inner triangles are similar, we can proudly bring in our area theorem. The ratio of the area of triangle APB to the area of triangle CPD is going to be exactly equal to the ratio of the squares of their corresponding bases. So that's AB squared divided by CD squared. As you can see, even when we are dealing with a complex trapezium, this fundamental theorem holds up perfectly. Now, to make sure you've truly mastered this concept, I have a little challenge for you. Take a look at this figure. Your homework is to see if you can logically fill in these exact boxes using both the AA test and the area theorem we've gone over today. I really want you to give it a try on your own. Before we wrap up this explainer, I want to leave you with a thought-provoking mathematical question. Today, we learned that for similar triangles, the area ratio depends on the squares of the corresponding sides. But what if two triangles are not similar, but instead they share a common equal height? How would the ratio of their areas change then? What exactly would it be proportional to? I really want you to think deeply about this. It perfectly sets up what we'll be tackling in our next mathematical exploration. Keep practicing your geometry, students, and I will see you in the next one.